Hi, I am Ana Carolina from University of Espírito Santo, and today I represent the work Study of the Influence of the Zirconia-Yttria content on the alumina matrix. Alumina is an engineering ceramic material used in biomedical and aerospace areas, and in structural applications. In machining, in which environmental conditions are severe, ceramic cutting tools made of alumina have abrasion resistance, high hot hardness, and chemical stability, which reduce the tendency to adhere to the workpiece materials during machining. However, the Achilles heel of the ceramic, working under mechanical loads and thermoshocks conditions, is the breathiness. And the failure under such service conditions is usually related to the low fracture toughness. One of the methods to increase the fracture toughness is the addition of stabilized zirconia to the alumina matrix, a ceramic composite known as zirconia toughened alumina. Zirconia has high strength and fracture toughness and a good wear resistance. The technique used to manufacture the composite was pulsed electric current sintering, known as PEX. This technique combines pulsed electrical energy and mechanical pressures to promote the transformation of a powder housed in the graphite mold into a solid form with the desired composition and density. This technique promotes fast sintering, high thermal efficiency, and uniform heating, and it's usually applied to advanced materials such functionally graded material. FGM is a kind of composite that promotes a gradual transition of the properties of different materials from one side to the other, reducing the mismatch of the properties of this material to a minimum. So, the objective of the study is to study the influence of zirconia stabilized with yttria content in alumina matrix. The samples were processed by PEX. The density and mechanical properties were evaluated and compared with a commercial ceramic cutting tool, and the results are intended to support the future development towards a functionally graded material. The materials used were ultrafine alpha alumina powder, nanopowder of zirconia stabilized with yttria, both from NanoAmor, and the commercial ceramic cutting tool CC620 from Sandvik. 4 samples with different pound volume fractions were defined. The volume fraction of zirconia in alumina matrix changed for each sample by 5, 15, 25 and 35% as shown in the table. For the mixture of powders, a precision scale was used for mass measurement and each volume fraction was placed in different bottles. The mixture of powders was performed in a liquid environment of isopropyl alcohol for 30 hours in a mixture, using grinding elements made of austenitic stainless steel. Then they were dried in a laboratory drying oven and deagglomerated in a mixer for 6 hours. The samples were sintered in a modern machine that have automatic cycle control of current, voltage, temperature, pressure, atmosphere, as well as displacement. The volume of the powders was arbitrated. The powders were manually placed into a graphite mold, and to avoid adhesion among powders, mold walls, and punch, a graphite sheet was used. The mold was placed between punches and electrodes of the machine, which promotes mechanical loading and electrode discharge at the same time. A uniaxial pressure of 50 megapascal and a vacuum atmosphere of 10 pascal was applied to the powders. The dwell time at the temperature of 1400 degrees centigrade was 7 minutes. The sintered samples were sectioned in half using a metallographic cutter. One of the parts was mounted in a manual compression mounting machine with bakelite to carry out the mechanical properties evaluation. The mounted sample had the apparent surface ground using silicon carbide powder, and then it was polished with a diamond paste. Micrographic images was performed in a scanning electron microscope. The other half part was reserved for density evaluation. Relative density was measured from this standard, which is based on Archimedes' principle. The Vickers hardness test was performed using the universal Wolpert durometer. The test was carried out following this standard, using a load of 10 kg force and computing values from 10 acceptables in indentation. The microscope Nicom Eclipse was used to visualize and measure the indentations and the cracks generated in the samples. The calculation of fracture toughness was performed by relating the Vickers hardness, modulus of elasticity, load, and average length of the cracks. The figure below shows the same images taken from the sintered samples. The white regions are fine zirconia particles, the gray region is the alumina matrix, while the black dots are porosity. In the figure, we note that zirconia particles are evenly distributed throughout the alumina matrix in all samples, indicating that the mixing step provides homogeneous powder. In this figure, we observe porosity dispersed throughout the sample, but as the zirconia content is increased, the porosity is reduced, as we can see in this sequence of figures. This graphic shows the relative density results for the 4 volumetric zirconia fractions. The porosity observed in the micrograph is related to the mean relative density value for the 5% zirconia sample. The results shows an increase in the relative density with increasing zirconia content, and considering mean density values, full densifications can be regarded from the 15% of zirconia volume fraction. With the increase of zirconia content was observed the decrease of hardness. This fact can be related to the lower hardness of tetragonal zirconia in relation to alumina, and also the greater capacity to transform tetragonal zirconia into monoclinic phase, since hardness is inversely related to the ease of transformation. The porosity of the sample with 5% of zirconia is another possible factor for the drop in hardness compared to monolithic alumina. However, the Vickers hardness number evaluated for the sample were higher than those tested, including the commercial ceramic. The results also show that the addition of zirconia in alumina matrix promoted an increase in fracture toughness up to a threshold value. There was a drop in this property with additional zirconia content, and using a reference value of fracture toughness, a parabolic behavior for the curve can be noted. The higher value of this property was obtained for the 5% of zirconia volume fraction. The improvement of this property is due to the phase transformation of zirconia from tetragonal to monoclinic phase. This phase transformation is accompanied by an increase in volume which induces compressive stress around the crack tip, preventing its propagation and developing the toughening effect. However, for the 5% of zirconia sample, some porosity level might have been able to absorb fracture energy, changing the fracture mode and increasing the toughness. The conclusion of this work is that the pack sinter technique proved to be efficient for the thermal treatment of aluminum zirconia composite, the samples reached complete densification. There was a decrease in the hardness value with the increase of the zirconia content, and the fracture toughness value present a parabolic behavior. Although the sample with 5% of zirconia had about 8% of porosity, it had a higher weaker hardness and fracture toughness. The results contribute to develop a functionally graded ceramic to be applied as a cutting tool with optimized zirconia content.